Hello everyone, welcome to yet another lecture series on basics of electrical engineering. In this video, we're going to talk about behavior of a PR resistor in an AC circuit. So let's get started. So resistor is basically a passive element. Along with it, other passive elements are inductors and capacitors. So the reason why we are studying this is because there are certain aspects with respect to behavioral factors that are concerned with respect to these devices. Without understanding them, we can never apply them in electrical engineering. So that's the reason why we'll be studying what is the behavior with respect to AC circuit for a pure resistor. Because when you say AC, the fundamental terms such as power factor, the phase angle differences, all these comes into picture, and it is not like a simple DC circuit which contains a DC source and a resistor. There are a lot of other factors involved. So let's get started. Let's look at the various factors that we are going to discuss about. We're going to talk about the nature of current, the waveforms with respect to voltage and current for a resistor. We're going to check how the phasor diagram looks like, what is the impedance offered with respect to a pure resistor, and what is the phase difference. We're going to check what the power factor is also associated with a pure resistor for an AC circuit, and at last we're going to calculate the power. So let's get started. We will be considering the circuit, an AC source connected to a resistor in this particular fashion. Let us assume VR is the voltage drop across the resistor and I is the current flowing through the resistor. So the supply voltage with respect to AC analysis is V is equal to Vm sin omega t. So we are supplying a sinusoidal voltage, and we're going to check how the current is associated with it. So from Ohm's law, we know that I is equal to V by R. So I'll be writing the value of V, that is Vm sin omega t over here, divided by R. So Vm by R can be written as Im according to Ohm's law again. So you'll be getting I is equal to Im sin omega t. So what is the conclusion that we can draw? If you observe this equation, V is equal to Vm sin omega t and I is equal to Im sin omega t. Sin omega t is the quantity that is associated with both these terms, and that clearly indicates the phasor difference between these two is equal to 0. Therefore, for a pure resistor, both current and voltage will be in phase with respect to each other, because there is no phase difference. If this was sine and this was cos, then there is clearly a difference of 90-degree with respect to each other with respect to phase is concerned. But over here you have the same quantity associated with both the equations with respect to voltage and current fundamentally. So that's the reason why both the current and voltage will be in phase with respect to each other. So once this point is cleared, I guess 90% of the understanding with respect to resistor will be cleared. From here on, we'll be looking at the waveforms associated with it. So with respect to the waveform, if you carefully observe, both should start at the same point and both should end at the same point, and both should have the phase difference at the same point. That means they are going to the negative direction at the same point, because the phase difference is 0 and they're starting at the same point. So magnitude, we're not focusing on the magnitude, that why is voltage very higher or current is very higher. We're not looking at that aspect. We're only looking at the phase difference with respect to waveform. So they'll be starting at the same point, they'll be crossing 80 degree 180 degree at the same point, and they'll be coming to 360 degree at the same point. That is equal to 2 pi here. So once this is clear, phasor diagram, let us consider V as the reference. So the current I is in phase with respect to V according to these two equations and our conclusion over here, isn't it? So we will be writing I in the same direction with respect to V. So that's the reason why both are represented in the same line in this particular direction. So the reference will be usually considered in this particular direction, that is indicated in the arrowhead over here. So once this is done, what is the impedance offered? Impedance offered here, we have a resistor element, so the impedance is nothing but the opposition of the entire circuit with respect to an AC circuit. If you're talking, impedance is basically the total opposition offered by the circuit. Resistance is particularly the opposition offered by that particular element, but impedance is a whole of the entire elements that are connected in the circuit. Over here we only have resistor, so Z is equal to V by I from the fundamental definition of impedance. So V can be written as Vm by Im because it's associated with the instantaneous values, and Im is can be written as Vm by R according to Ohm's law, and this equation over here that is represented, you'll be getting R. So basically the impedance offered for this particular circuit is the resistance itself, R. So this is an important point to be observed as well. Once this is done, what is the phasor difference? So phasor difference is 0, as we have already seen in the previous slides. That is, we found V is equal to Vm sin omega t and I is equal to Im sin omega t. So phi is equal to 0 because there is no phase difference at all between those two two quantities. So whenever we are talking about phase difference or waveforms or any power factor, it is always with respect to voltage and current relationship. So these are the fundamental quantities in which we will be comparing the various values that are associated with them. Once that is done, the power factor associated. So from the definition of power factor, it is defined as the cosine of the angle between the voltage and current phasors. So what does that mean? Cosine of the angle between voltage and current is nothing but phi. So phi is the angle between the voltage and current, and cosine of the angle is cos phi. So cos phi is the power factor. We will be representing it in terms of power factor as cos phi. So cos of 0, because the phase difference is 0, substituting, you will be getting 1. So power factor for a pure resistor will always be equal to 1. So ideally this will be our requirement with respect to any circuit. If you're talking about a resistive network, we will be ideally achieving a power factor of 1. That is our aim with respect to circuit analysis for a pure resistor. So once that is done, we're going to calculate the power. So instantaneous power, according to the definition of power by Ohm's law, that is already seen in one of our videos. So in case if not watched it, please do watch it. The link will be provided in the description. So power is equal to V into I. So from the fundamental definition, can we write V as Vm sin omega t, because it is taken with respect to AC supply that we are giving, and I is the current that is flowing through the circuit, that is nothing but Im sin omega t. We have already found why it is Im sin omega t in our previous slide. So substituting for that, and I will be rewriting the value of this quantity. Sine into sine is multiplied, that is sine square omega t. Vm Im is assembled together, and now what I'll do is sine square omega t can be written as 1 minus cos 2 omega t by 2, that is by trigonometric relationship. So further that can be simplified as Vm Im by 2, multiplying it inside, and again minus Vm Im by 2 cos of 2 omega t. So this power basically has two quantities. This is the constant term which does not have any other quantities associated with it, and this is f term that varies with respect to a wave, that is nothing but cosine wave over here. And if you carefully observe, the frequency is twice as the fundamental frequency, because you have 2 omega t and not only omega t. So the power consists of a constant part and a fluctuating part. The reason why it's called as fluctuating part is because the cosine wave keeps on changing its magnitude every instant of time. So that's the reason why it's called as fluctuating part. And Vm Im by 2, once you know Vm, once you know Im by 2, the value always remains constant. That's why it's called as a constant part. So now what we're going to do is, I've kept the relation with respect to the previous equation. So average power P is equal to Vm Im by 2. So Vm Im Vm by 2 can be written as Vm by root 2. Im by 2 can be written as Im by root 2. I mean, what I'm trying to say is, when you multiply these two, you will be getting this only. So Vm Im by 2 can be written as Vm by root 2 into Im by root 2. Root 2 into root 2, you will be getting 2. That's the reason why we can split it in this form. The reason why we are splitting it in this form is because we are trying to represent the average power in terms of RMS value. So average power can be written as P is equal to V into I. That is nothing but the average power over here, because V is taken as Vm by root 2, I is taken as Im by root 2. V and I are nothing but the RMS value. So the power in a purely resistive circuit is equal to the product of RMS values of voltages and current. So I've not represented current over here, but add that statement as well. So it is basically the product of the RMS value of voltage and current for a pure resistor. So I guess this concept is clear. Once this is done, we will get into our next concept with respect to capacitor and inductor in our upcoming videos. In case you have any questions with respect to this particular analysis, please do write down your questions in the comment section below. If you like this video, please do like it and subscribe to our channel for regular updates. Thanks for watching this video. Thank you.